Just 1 second. Actually, so the slide advance will only work if this is Zoom. So instead, just use the power. Just use this. Yeah, and then just advance right here. Okay. Hope everybody found some food not just a box lunch, but found something that was edible in there. We're going to start our afternoon session. Whereas the morning was more toward, let's say, visioning and tutorial. We had great talks in that area. The afternoon is going to be a little more focused on case studies. We're going to see where in the field of material science we've used some of these things. And we're going to start out with, it's my pleasure to introduce Ankit Agrawal. He's a research associate professor at Northwestern University. I've worked with him on grants before. This is my first time meeting him in person, so it's a treat to meet you in person. And I'll say that he has expertise in a variety of areas, not just in material science. So I knew him from working what's called ICME, which is a type of it's a group of people in material science trying to solve using big data in material science problems. But he also does work in, say, like healthcare and in social science. So I think that, I don't know how much of that will be here, but maybe he can tell you a little bit about that, and we're excited to have him here. Thanks, Ankit.
All right. Thanks for the encouragement. So first of all, thanks to the organizers for inviting me. I'll be talking about materials informatics and big data, which I describe as the realization of fourth paradigm of science, and I describe all these things. Important to note for you that I am a computer scientist. I am not a material scientist. So actually, I'd like to know, is there any computer scientist in this room? Okay, so I have some company. Actually, it's good that over the last 4 or 5 years that number is increasing. So my goal is that the next 5 or 10 years there'll be much more participation, because that's what is needed for this field to grow more. So most of the work that I'll be describing today is in collaboration with the material scientists, mechanical engineers, chemists, civil engineers, and so on. So I'd like to acknowledge them here, and it's a privilege to work with these experts. They're world leaders in their fields. Also, these are the funding agencies that have supported our work. So let's begin. So coming from a computer science background, this is what we do. In this era of big data, I strongly feel that data mining and high performance computing, these are two fundamental technologies or subfields of computer science that need to come together more than ever before if we are to address the big data challenges. So what it means is that when data size, velocity, variety, all these grow up exponentially, we need to be able to mine insights, so we need data mining, but we also need to be able to do it faster. So we need high performance computing methods to develop scalable algorithms which can work on not just tens of hundreds of thousands, but millions or billions of data points in some cases. So that's why I call it high performance data mining. And then I'm personally very interested in applying these in multiple domains like materials, social media, healthcare, climate, astrophysics, and so on. Of course, in this talk I'll be focusing on the materials aspect of our interdisciplinary research. And the reason we became interested in this is, I'm sure everyone here knows, is this Materials Genome Initiative, which was announced in 2011, where the goal is to deploy advanced materials 2x faster and 2x cheaper. And data-driven analytics was specifically identified as one of the key techniques or key set of techniques to play a major role in realizing this vision. So as part of this effort over the past 4 to 5 years, we have several funded projects in MGI. We are part of the NIST Center of Excellence. Actually, I'm co-leading the data mining efforts across the center, which is a 5-year, $30 million center from NIST. There is an Air Force project, MURI, which is focused on the microstructure aspects. There is a DARPA Simplex project, which kind of it's kind of ended now, but it was focused on thermoelectric materials, and that's where we work with Dale Sparks here. We're also part of the NSF Big Data Spoke, Northwestern Data Science Initiative. This is an internal Northwestern mechanism for promoting data science research at Northwestern. We're collaborating with Greg Olson on steel alloys in this project. And then recently there has been a lot of interest from the industry. A lot of people have approached us for working together and so on. And it is one such relationship which has been recently formalized with Toyota. So this is going to be the overview of my talk here. I'll start briefly with some basics and just background about materials informatics and big data. And most of my talk will be presenting illustrative examples from our group, because that's what I was asked to speak most about, and then I'll try to demonstrate some of the tools that we have developed. So let's begin. So if we look at the advancements and the progress of science and technology as a whole, not just in materials, not just in one specific field, and not just in terms of years but centuries, we can identify these 4 paradigms of science very easily. So till about 17th century, all science was purely observational or empirical. Everything was based on observation. You look at the sky, you look at some material stones, or you get some insights and so on, which is today famous as the experimental branch of science. Then in the 17th century, with the advent of calculus, we could take these real world phenomena and formulate them as mathematical equations. So very good examples in materials field are these laws of thermodynamics. But over time, these models became larger. And when computers came into being in 1950s, we could solve these equations, much larger systems of equations on computers, and now supercomputers. So the third paradigm of science, which is simulation-based or model-driven science, that became popular, and things like DFT, molecular dynamics, finite element simulations, these are very good examples in the materials domain. Over the last couple of decades, the data that these 3 paradigms have been producing has far surpassed our capacity to make sense of it. So even as computer scientists, we have made a lot of advancement in collecting data, in storing data, and retrieving data. So the hard drive sizes are going up, and they're becoming cheaper and more reliable, RAID technology and so on. But we are not able to keep up with analyzing it and deriving actionable insights. So that's why this 4th paradigm of big data driven science becomes has become very popular. Things like predictive analytics, clustering, relationship mining, anomaly detection. These are some of the key techniques which help us to uncover insights from this data. Important thing to note here is that both 3rd and 4th paradigm of science are based on computation. They rely heavily on computers. But the key difference is that in 4th paradigm, the data itself is a resource in addition to the computation. So it can complement our physics-based models or whatever domain knowledge we have. Just because of the amount of data that we have collected historically, that can help us identify patterns and make decisions. So okay. So again, those who are from computer science, they will, maybe all of you, most of you will know these are different V's associated with big data. And some time back it was a fashion to introduce your own V. If you want to become famous in computer science, you just put your own V there. But these 3 V's are kind of the differentiating features which differentiate big data with other kinds of data. So big data is high volume, high velocity, high variety, or all 3 or 2 of them, and so on. And then other things like variability, veracity, these are features of all kinds of data, including big data. So the goal, of course, here is to mine this data in different ways to extract value or hidden insights or needle in the haystack, whatever you want to call, and visualize in suitable ways. There's another definition of big data, which is probably more pertinent to materials. That was found in one of the grant proposals. That big data was defined as where the data is significantly larger compared to what it has been. So we definitely don't have in materials. We don't have billions and billions of data points like Google, Facebook, social media may have. But over the last few years with MGI and these federal initiatives, the amount of data is significantly going up. So in that sense, it is big data, and I'll give you one very good example in the later slides. So this whole thing is nothing short of finding needle in a haystack, and I like this example very much because it signifies not only the difficulty in finding the needle in the haystack, but also the ease of being able to find the wrong needle. What it means is that if you are not careful, and careful is multidimensional here, if you're not well conversant with the strengths and limitations of your data, strengths and limitations of your techniques, experiment simulations, then you can very easily fall into this trap of blindly applying, just marrying the two together, the data and techniques, and getting some numbers out of it, and think that it is discovery, but it's not. So, okay, so moving in the material science domain, if there's one thing I've learned from our collaborations in material science, That is that everything or almost everything in material science depends on these so-called PSPP relationships. So processing, structure, property, performance, where the science goes from left to right and engineering goes from right to left. What it means is this is the left side is the cause and this is the effect. So processing affects structure, it affects properties and performance. And if our goal is to get a material with high performance, the means is to work on the processing and structure. Interestingly, these are many-to-one relationships, and this is very fascinating to me because in my PhD I worked on bioinformatics a lot, and there we have something called sequence structure function relationship. So it's a DNA sequence, you get protein sequence out of it, protein structure, and then protein function. So this is quite it's a good parallel in materials, and here these are many-to-one. What it means is that there are many different processing routes in the processing space which can lead to the same structure. So theoretically, you can have structure, you can beat it first and then heat it, or vice versa, and there are different processing routes. Theoretically, they can all achieve the same structure. And the same property can be achieved by multiple structures. So there can be different materials which all optimize or they have the same property. For us, what it means is that the forward models are easy. Easier, not easy, but easier. Because for a given material, there is only one property. But the inverse models are much harder because for a given property, there can be many different structures, many different materials, and ideally you want to be able to identify all of them or most of them, because some of them may be more machinable or easy to make in the lab or cheaper and so on. So it's not just sufficient to find one material which is you can't create in the lab. So materials informatics, which is essentially application of data mining in the field of materials, it can help us generate these fast and accurate forward models where you can represent property as a function of some representation of the material, usually processing, composition, structure, and then if these are accurate enough, they can help us realize the inverse models of optimization and design, because essentially the inverse problem is an optimization problem, right? So you want to optimize some property with some constraints on the structure or composition, and any optimization problem, as you'll know, it deals with multiple invocations of the forward model. So think of the forward model as a proxy to the experiment or simulation. So if the experiment was dirt cheap, you could just do all the experiments and find the best solution. But you can't do that, and you even can't do the simulations that fast for some cases. So if there's a fast and accurate forward model, you can just use it as a proxy to kind of explore the composition or the material space and get to your answer faster. And I describe all this in this invited article. If you are interested, you can take a look, please. So the overall vision, the grand vision that we have here is to combine all different data sets from experiments, simulations, processing, structure, property, and combine this into this heterogeneous materials database. So that's something like what NIST is doing, MDF, and what Bryce described in for the citronation, and then using a series of supervised and unsupervised learning steps, of course applied with caution. The goal ultimately is to get knowledge, which in the case of materials is invertible PSPP linkages. So since invertible is very important, because we just don't want the forward model to be accurate enough, and that's not sufficient. We want to be able to do material design, discovery and design. So these relationships have to be invertible. So that's the overall goal. So now I'll be talking about some of the illustrative applications that we have been working in the last few years in terms of forward models, inverse models, and structure characterization. Structure characterization is technically an inverse model. It's an inverse problem, but I've listed separately because it has some unique characteristics, which we'll see in some time. So here is a snapshot of the kind of things that we have done. So for the forward models, which is essentially prediction problem, we have made models for steel fatigue strength prediction, for formation energy prediction, band gaps, glass forming ability, bulk modulus, Seebeck coefficient, and then homogenization and localization relationships, which are essentially mimicking finite element simulations. And we have taken some of these models and realized the inverse models of optimization and discovery. And these are some examples of stable compounds, magnet-restrictive materials, semiconductors, metallic glasses. And then last couple of years, we have also been doing some image or structure characterization with image data, for example, EBSD indexing and crack detection in macroscale images. So my goal in the next, of course, each of these is a 1 hour talk in itself. So I won't go into details of either of these, but I'll try to present a high level overview of some of these and then hopefully if there is interest, I can dive deeper. All right, so this is one of the first projects that we started back in 2013, I guess, where we're looking at experimental data of steel. So here we have around 400 data points from NIMS Japan of experimental fatigue strength. Of course, I don't have to go to the significance, why it's important, and so on. But the goal was to develop forward models for this case. This is what the data looks like. There are a bunch of composition parameters like percentage, weight percent, carbon, silicon, manganese, phosphorus, and so on. And there's a lot of processing parameters like normalization temperature, through hardening, cooling rate, carbonization, and so on. And it also has this fatigue strength, which is the property of interest, and we want to be able to predict this fatigue strength with good accuracy. So this was a long time ago, as I said, with a traditional supervised learning framework, with pre-processing, feature selection, predictive modeling, evaluation. We developed models, accurate up to 98% R square, and then recently, a couple of years ago, then we improved on these models because this was the best model from this paper, which by the way became highly accessed in a very short time, because back in 2014 these kind of techniques were very new in material science. So there was a lot of interest in this work, and but this was the best model there, and you can see for low carbon alloys the model miserably failed. Then with advanced ensemble techniques later we kind of fix this problem where we get numerically it's kind of hard to beat this, but we can see that for low carbon alloys the prediction is much more accurate. And we also kind of deployed the best models in a tool where you can go and just put the steel of your choice and get the predictions, and with all the uncertainty estimates of the prediction for your steel. So that's an example of and actually one more thing I want to highlight here. This 400 or so data points, this is actually very small data compared, from our perspective, because we are used to dealing with in astrophysics and social media and so on, like billions and billions of data points. But for material science, this is actually big data, because NIMS Japan, it took them 50 years of hard effort to come up with this, because you have to really make the steel and break it, and it's not easy to get this kind of data in material science, experimental data especially. So when the data quality is good, and we can do some good predictions. This is another example from the simulation domain. So here we are using DFT calculation. This was actually this is ongoing collaboration with the Voronoi group who hosts the OQMD. And it's kind of interesting that this was actually the first project that we did, and at that time Bryce was at Northwestern. He was doing his PhD, and I remember he one day approached us, and we sat in my office, and he said that I have a crazy idea, because at that time no one thought about machine learning, and he said that we have these DFT calculations that our group has been doing, and what if we can do some machine learning? So I remember we had 26 iterations of data back and forth before we could actually agree that okay, this is a publishable model, we can go ahead and start writing paper on it. So that communication gap, it took like 2 years for us to understand their language and them to understand our language, and then finally once it was published, then the next paper took just 6 more months. So this communication is very important. So getting back to this work, here we are using DFT simulations, which are very slow and require crystal structure as input. And the goal was to make forward models and inverse models. So these are some of the composition derived attributes that you can come up with. So let's say for ferric oxide, you can calculate all these different things, which I think in the previous presentations were already considered. So Bryce came up with this set of 20 or so attributes, and this combined with elemental fractions. This served as a representation for the material. So this is, let's say, OQMD, and using some supervised learning technique, we get this predictive model. Now for the inverse models, we took the entire space of unexplored ternary space, basically. So all compounds of the form AX, BY, CZ, all possible elements, all possible fractions, with some caveats, of course, and then scanned this set of materials through the model. Because this model is very fast and accurate. I should mention the model accuracy was about 0.1 electron volt per atom, which is kind of at par with DFT's own accuracy compared to experiment, which means that with this model you can, in the worst case, go twice as bad. In the best case, you can come back to the truth. Of course, there are extreme cases, but it was kind of encouraging to see that the accuracy is of the same order. So now we can take this set of materials and convert them into a rank list, because this model can scan millions of compositions in just a few hours. So then we can look at the top ranked materials and then appropriate selection and validation experiments you can do to do material discovery and feed it back into the data set and just keep improving. Here are some of the top predictions with across a range of chemistries that were confirmed to be stable by crystal structure prediction and DFT calculations. So again, at that time these were very new techniques. So this work represented the first effort which discovered about 5,000 new materials which are stable. Then we kind of built on it further. This was one follow-up work where another student of Crystal Wharton, Logan Ward, he basically expanded this attribute set. So instead of just these 20, he just took the handbook and threw in every property that you can think of. So there's a set of 145 composition-based descriptors which are based on stoichiometry, elemental properties, electronic structure, and ionic character. And the important thing that this work showed was that this set of attributes, or this representation, was quite powerful for modeling very different properties. So usually for some property, let's say band gap, some researchers will throw in some attributes that they think are important for band gap. Performance energy, it may be some different set of attributes. But because this was kind of a thorough search, of course, it's not exhaustive by any means, but it was shown that this model can work well for band gap prediction, like for solar cell applications, as well as for metallic glass formation, amorphous metal alloys without any modifications. So what it means is now anybody can take this software, and this is all available as part of this open source MagPi software. You can take this, take the software, get these 145 attributes for your data, and build machine learning models on top of it for any property. And here are two examples. For the glass forming ability, we kind of withheld this system, nickel, zirconium, aluminum system, from the training data set, and not just this ternary system, but also the 3 binary systems. So there was the training data did not have any nickel, zirconium, aluminum, and aluminum, nickel compositions in the set. And then we asked the machine model to just fill the space, and you can see that it is a reasonably good match with the experimental. And some of these have been confirmed experimentally in collaboration with SLAC and NIST. Then the same set of attributes were was also found to be powerful for semiconductor applications. So like for predicting band gap. And here are some new compositions that were discovered, or candidate compositions for further experimentation and simulation. So this is one follow-up work where we are trying to add more and more chemistry knowledge into the model in terms of composition. But we just saw that we have processing, structure, property, performance. So structure is important. You can't get away with it. So these models are composition based. You don't need any structure information. But we know that the same composition can have different structures, and they will definitely have different properties. So in another follow-up work, we try to incorporate the structure information, the crystal structure information, into the model by using, which many of you may be familiar with here, called Voronoi tessellation. So what it does is, actually the figure is not complete here, but what it does is it takes the crystal cell, and then for each atom, it creates a Voronoi cell like this. So so there are 8 sides to this, if you see. So each of the sides correspond to a neighboring atom. And for each of them, you can calculate things like coordination number, bond length, and so on. And these can serve as the structure representation of the material that you give to the model to learn your models on. So below you see 2 figures here. This red curve is this work, and we compare it to 2 state-of-the-art approaches which are structure aware. So the PRDF matrix approach and Coulomb matrix approach, and you can see that as you increase the training data set size for big data sets, this approach is much more accurate and faster, both for training and testing. So as you put more and more data, you can have faster models and better models, both in terms of training and testing. So of course, this has applications in terms of reducing, if not replacing, DFT calculations, because now you can, for a new composition, you can just try all possible structures and give it to this model and see which is the best property that comes out of it. So you don't have to do all the DFT calculation. It can significantly reduce the number. So this was the second follow-up work. So as I described, one thread of research that we are doing here is how can you put more and more chemistry into the model, and that is of course makes sense because in the earlier talks we saw how representation plays a major role. So if you can put more and more composition-based information, structure-based information, we expect the model to improve. But as computer scientists, we are also interested in something diametrically opposite. What if we don't use any domain information? Because assume that we are just ignorant of all chemistry, or we just want to use the simplest possible representation, which is just the element fraction. So using deep learning, and actually I was expecting that the morning talks to have some introduction on that. So I don't have slides on deep learning here. I do, but not in this presentation. Deep learning, essentially, for those of you, I mean, everyone must have heard of it, but I just want to give a little bit background. Deep learning is essentially a rediscovery of neural networks. So what it means is that neural networks have been there for 50 years, and it kind of became popular in 80s and 90s, but it didn't really go overboard, because there are three keys to deep learning: neural networks, big data, and big compute. So you need all three for it to work. So we had neural networks, but we did not have big data and big compute. But now that we have big data and big compute, it has shown that using just raw representations, so like things like image recognition, we can just give the images without any manual feature engineering or any hand engineered attributes, and it can do remarkably well. So what we try to do here is, can we do the same thing here? So we only want to give the fractions. So if you go to the previous thing here, we are not even giving all these chemical derived attributes. We are only giving the fact that for this ferric oxide, it is 40% iron and 60% oxygen. That's it. And then let's see what it can do. So remarkably, we found that if we have sufficient data, and of course now we have big compute, we can have more accurate and faster models. So this is the typical trend you see when you compare deep learning and traditional learning algorithms. So for small data sets, deep learning is often not that good. The traditional algorithms like decision trees and Bayesian networks and so on, they can often do better. But there is some crossover point, and this depends, of course, largely on the data set, the problem, after which the accuracy of most learning algorithm kind of saturates, but deep learning doesn't saturate that early. Of course, it will saturate at some point, but what the trends have been that as you put more and more data, it can keep improving. So for this problem, interestingly, we found that this crossover point is just a few thousand of compounds. So it was very surprising. Typically, it's thought that we need millions and at least hundreds of thousands of data points. But for this, just around 4,000 data points was sufficient to beat traditional algorithms. And these algorithms, the final model that we have are like 20% more accurate than the state-of-the-art model, and because they can be run on GPUs, they're also 2 orders of magnitude faster. And there are some very recent results that we have got, where we have seen how these models are behaving with different inputs. So I don't have it here, but you can just think of it. These models don't have any periodic table information, right? It just has a bunch of 100 size vector, just the fraction of elements. But we gave this model different elements and different combinations of element, and we found that somehow this model was able to treat, let's say, lithium, sodium, potassium, cesium, all of them in a similar way compared to other elements. So we didn't tell that these are all part of one group, but this model kind of figured it out by itself. And then it also figured out, like, for example, we gave it NaCl and MgCl, and it could figure out that, okay, all charge balanced compositions were actually clustered together, and not charge balanced were somewhere else when we looked at the activation graphs. So it was kind of very exciting. that this model can actually learn chemistry for the first time, where we can be confident that this can be good prediction. We also made other tests. Of course, I don't have because these are very recent results. Just last week we got, so I don't have the figures here. But the thing I want to highlight here from this slide is that deep learning models are up to an order of magnitude faster and much more accurate, at the cost of one-time training costs. So it costs a lot to learn these weights, but once you have learned them, you can make predictions much faster and much more accurate. And here we have compared with the random forest model with different number of trees, and the nearest neighbor approach, which just takes the most similar compound from the training set and gives the prediction. So this is all from the DFT space. Now let's move on to the thermoelectric space. Here, this was part of the Simplex project. So here we are using experimental data from the UCSB database that Taylor had developed, and also the T-designed database for another property. So for any of you, if you know anything about thermoelectrics, you know that what is ZT? It's the figure of merit for thermoelectric materials, and it depends on the Seebeck coefficient, temperature, electrical and thermal conductivity. So as of now, we made models for Seebeck coefficient and bulk modulus, which indirectly goes into this formula. And using composition and production aware attributes, you could get R square up to 0.84. And here you see the scatter plots. And we have added these models to our thermoelectric toolkit, where you can put in a compound and get predictions for Seebeck coefficient and bulk modulus. One interesting thing that we found in this was outlier analysis. So Taylor can correct me if I'm wrong, but I think this data set was extracted from literature, right? And a bunch of undergraduate or some students were kind of paid some pizza to build it.
That's exactly what happened.
Yeah. So we found that our model was performing very bad in some cases. So the postdoc who worked on it couldn't really stop herself. She went back to the papers and found what's going on. So we found many of the cases where the model had failed, the data collection was erroneous. So sometimes, like Seebeck coefficient is a polar quantity. So sometimes the sign was missing. Sometimes the magnitude was wrong. It was some other figure taken from the paper. So this kind of it was a finding that we were not looking for, but it was kind of a pleasant thing that if the majority of your data is good. So if all of your students are drunk, then nothing can be done. But if majority of data is good, then we can use the data mining models to kind of do data curation effectively, which can help in further modeling. So here's the tool. At this link, and in the end I'll try to show it. So let's move over to the microstructure space. So here we are looking at this is a collaboration with Veera from University of Michigan. This was part of the Muri project, which is on microstructure. Here we are looking at magnetoelastic alloy, Galfenol, iron gallium alloy. And just like thermoelectric materials can convert heat and electricity, these materials can convert force and magnetic field. So if you apply force, the magnetic domains shift and rotate so as to produce a magnetic field. And if you put it through a magnetic field, the material kind of elongates and contracts and so on. So these have very good applications in actuators and sensors. So the goal here was not the forward problem. It was the inverse models were more challenging because the forward models are known. So given a microstructure, we can get the property easily using homogenization methods. The way to represent microstructure here is something called the orientation distribution function, which is just a distribution of the different orientations. So given a structure, we can get the properties easily, but the inverse models are very challenging because it's an optimization problem, and it's very high dimensional. So compare this with the DFT example, where we just scan all ternaries. So there we had 3 dimensions, like AX, BY, CZ. So there are like 100 elements in A axis, B axis, C axis. So there are million compositions, and then with different stoichiometries, you can maybe have maybe billion, let's say. But in this case, we had 76 dimensions because microstructure is a continuous space, and the orientation distribution function was represented in 76 dimensions. So even if you assume that there are only 2 possible values for each dimension, and if you assume that the forward model is ultra fast. Just it takes 1 microsecond. Just enumerating 2 to the power 76 combinations will just take you billions of years. So you can't do that. You can't do the approach of just scanning everything that we did in the case of DFT. So what we did, instead of traditional optimization, we came up with this data-driven optimization, which relies on these 3 steps: random data construction, search path refinement, and search region reduction. What it does is, among those 76 attributes or 76 dimensions, it tries to find that which of those 76 are most influential in increasing or decreasing my property of interest. And then let's say we find a subset of top 10. Then within those top 10, we want to identify which space of the microstructure, let's say it's normalized between 0 and 1. We want to identify that which space is most promising, and then focus our search power in that space only. So when we did that, and there are details which I'm skipping here, we found up to 80% faster model and 20% better in terms of the optimal value. So there were 5 properties that we were kind of optimizing here: the elastic strength, the yield strength, the magnetostrictive potential. I don't have listed here. I should have probably, but and composites of those, because some of the properties we want to maximize, some properties we want to minimize. So we can take composites of those so as to for example, if you want to maximize A and B and minimize C, I can try to maximize A into B by C. So using that and some other ways, we came up with many solutions. And this was the most attractive part, which was very exciting to our collaborators, that multiple solutions were derived for the first time for this problem. So if you remember the PSPP relationships, the inverse models are many to one. So for 1 to many, inverse is 1 to many. So for a given optimal property, there can be many structures. So it's important to find many of them. And here you see like 27 different orientation distribution function representations, which all maximize a certain property. This was published back in 2015 in Scientific Reports. And then recently what we have done is we have devised some feedback-aware sampling strategies, where we have increased this number from 27 to thousands. By so what we do is we have some tolerance parameter where let's say the optimum value is normalized 100. Let's say if we have some other material which is 99.9998, that is still good enough for most engineering applications. So we have some tolerance like a 0.01%, and then when we do that, we can get thousands of different representations like this, which of course we believe that some of them will be more readily machinable in the lab and so on. So that was just recently published in the Aeronautics Journal. Some more from the microstructure space. This is finite element simulations, mining, data mining on that data. So this is a localization problem, right? So you have a 2-phase composite, and you can, for a given load at the macro scale, you can find the distribution of that in the micro scale like this using finite element simulations. And these can take minutes, hours, weeks, depending on how refined this mesh is. So using a context-aware machine learning approach, we build multiple regression models for different contexts. So here you see that this is the ground truth of the most difficult RVE or cube in simple terms. And these are different context detection methods. So you can group your data sets by volume fraction. You can make different models for different volume fractions. You can make different models for different, you can do some data clustering, or you can do clustering based on 2-point statistics. So as you define your structure more and more, in different ways, we found that this 2-point statistics approach gives the best accuracy in terms of, you can see that these hotspots are kind of preserved here. So for a new microstructure, what it does is that it will take the 2-point statistics. It will find which of these clusters it belongs to, and then use the corresponding model. So it's like a hierarchical machine learning approach, where you are using different models and ultimately predicting the response at the voxel level. That's localization. You can also do at the entire cube level, which is the homogenization, and that's also something that we have done, which is under review right now. And this, of course, by the way, is big data, because each voxel is a data point. So let's say we have 10 by 10 by 10,000 voxels per cube, and we have, let's say, another 1,000 data sets. So there's a million points right there. In this case, we had, I think, about 25 million points based on our parameters. And this can reduce the, it can serve as a fast approximation to FEM, reducing the 45 minutes for this, reducing it to just less than 1 second plus a one-time training cost. So that's about finite element simulations. In the image space, we have looked at electron backscatter diffraction images. So I don't have to give the introduction of what EBSD is. That indexing problem, of course, this is in collaboration with Mark de Graaf at CMU. So the indexing problem is, given image, we want to find that which crystal orientation it came from. So in the Euler space, you can represent it by 3 angles, phi 1 and phi 2. So we developed a deep convolutional neural network with a customized loss function, which can exactly do that. Take this image and give these 3 angles. And the loss function had to be customized in this case because although it's a number, these angles are numbers, but these are not like ordinary numbers. So 1 degree is very close to 359 degree, right? So you can't just use mean absolute error or something like mean square error to optimize this. So we use this cos inverse of cos of the difference, which maps everything into 0 to pi. And then this is the nearest neighbor approach, which currently they use. They call it the dictionary-based approach, where you get a new EBSD image, you just do a dot product of that image with your dictionary, which has all possible EBSD patterns, and then find the closest one. So these are the kind of errors you get with that approach, and with deep learning you can get much better and faster, at the cost of training, of course. So the nearest neighbor approach, there is no training time. Why there is no training time?
It's just a table lookup.
Yeah, there is no model. The data itself is the model. So you don't have to build any trees or anything on top of it. But in this case, you have to build the neural network. So it takes a significant amount of time. But once you do that, it's very fast. And then we have tried to apply these techniques in macro scale images. So those are all microstructure, micro scale images. Here we are looking at pavement images of, like this. So this Federal Highway Administration, it has this program where it collects these kind of images, and the goal is to find places or stretches of the roads where there are potholes or cracks and so on, which need more attention before an accident happens. So we took a small subset of the database, which was classified as crack and no crack. This is a labeled data set, and here we're using transfer learning for these models, because this is a small data set comparatively. So deep learning works when you have big data. So either you need to have big data directly, or you need to have big data through some transfer learning approach. So you use a model trained on some big data, and then use it on a related problem. It doesn't have to be exact the same problem. So in this case, we used the ImageNet, which has around 15 million images of all these day-to-day things like cats, dogs, airplanes, and houses and on. And this is a pre-trained VGG16 network, which has been trained on that. We use this network and then ran these images on it to get the features. So that became the representation for the machine learning model, and then we can get up to 90% accuracy because of this transfer learning, because the VGG model has already kind of learned the underlying representations of how images are exist. So this is an example on pavement, and then recently, it's a very recent work, we tried the same thing on drone images for structural health monitoring. So in collaboration with a drone company, it has these drones and it can take images of these structures, buildings, and so on. And note that the data set is even smaller here. So just 130 images, and of course there are 80 and 50 cracked and uncracked. And using a similar thing, we can again get up to 90% accuracy for this problem using transfer learning. So I hope that I have provided a kind of some snapshots of these works that kind of use data-driven science in different ways at different levels for different kinds of data. But ultimately, the goal is to get these relationships at different levels. So how much time do I have?
If you want to save time for questions, you got about 5 minutes.
Okay, so I'll just give a quick demo of these tools. So there is Wi-Fi here. So you can go to this website, info.ecs, and this has many of our tools in different domains, of course. Okay, so I'd like to maybe just give one example of material science here. So there is the steel data. So here you can put your choice of steel with composition and processing parameters, and it can give you predictions in real time with uncertainty. And these are specific uncertainties, so if you change something, let's say you'll change the prediction and uncertainty, of course. So this is not just the mean absolute error or RMSE. So you can have specific predictions. Also, if you do not have all the attributes, there is a reduced attribute set which you can use, which, you know, these were the most influential attributes that went into the model, and you can again do the similar thing. And these are all the histograms of the error bars and actual and predicted values. This is the formation energy thing that we had. So currently we have deployed only the composition based models here, although the software is available for the structure as well. So here you can put a bunch of compositions, and deep learning model is the most accurate. So we use that, and it can give you real time sortable table of the predictions. Then the Thermoelectric toolkit, as I said, there are two models for Seebeck coefficient prediction and bulk modulus. And here you can take things like the production method, the crystallinity, and the formula. And interestingly, we found that it works specifically well for doped compounds. So here you see non-stoichiometric compounds, and we get so it's a temperature dependent prediction. So Seebeck coefficient at different temperatures. So all of them are negative here. So you see that it's an N-type material, and similarly you can do it for bulk modulus. It needs a CIF file. I don't have one handy here, it's not my machine, but you can just put a CIF file like this, and it can make those predictions for you. All right, so of course there are examples from healthcare. If anyone is interested, you can take a look at them as well. You can put the patient information similarly, and you can get disease specific outcomes at different times. So this particular thing is for lung cancer, which is highly, which has a very low survival rate. So you can see less than 15% survive after 5 years. So it can give a progression of how the risk varies as a function of time. All right, so I think PowerPoint crashed for some reason.
Looks like it did.
Well, I was almost done anyway, so is there any questions?
Let's take questions then.
Yeah. I mean, I have one last departing message. So this is what I found. Of course, this is not everyone knows this, but this is what I really found over the last 5 years. We have tried numerous collaborations, and the ones that have succeeded are the ones where both us and material scientists, they kind of sat together on the same table, and understood or tried to understand the strengths and limitations of the data and the techniques, and then build customized solutions for these problems. So it's very encouraging to see more and more participation. Actually, I was at MRS earlier this week, and there were a few computer scientists in my talk as well. Along, of course, it was like 90% to 10% ratio still, but there was a joke that many people have asked that why it is difficult to attract computer scientists to this problem. So this is a very valid question, because in my own research and all, we find it very difficult to convince our computer science students to work on these problems. When we work in collaborations, the material science students from the other groups, they're very interested in learning these techniques and all. But I had really had to work very hard to convince my students to work on these, because they all want to work in let's say healthcare and social media and operating systems and more CS research. So for the first time in this MRS earlier this week, I found a talk from Google. So I've always used to say that when people used to ask why there is less interest from computer science, I used to say wait till Google gets interested in this, then everyone will follow. So now that Google has, they've been doing some very cool work in materials informatics. So I anticipate more and more participation from CS over the next coming years. So thank you so much.
Do we have questions from the speaker? Yeah, Tony.
So, from what I understand of deep learning, and specifically the chemical compound prediction, the one that you just showed us, a lot of it talks about how you still have to be agnostic of distilling any information from the deep learning neural networks. And so I'm wondering, like, if any of these projects try and address that problem of the no free lunch problem with deep learning, and that I'm wondering if any of these projects try to address knowing what parameters are correlated and trying to open up the black box of deep learning.
I'm not sure if I understand the question fully, but are you asking why deep learning is understanding the periodic table?
Well, so a problem I understand of big deep learning is that it does have a big black box problem, and so I'm wondering what if any of these projects have been trying to address the black box problem with deep learning.
Well, it's a black box problem if you don't address it. That's all. It's not so. As I think one of the speakers had mentioned, there is a explainable AI thing. So you can actually devise you can constrain your models in such a way that you put the domain knowledge into it, or you can interpret the model just like we have done. So you give it different combinations of input and see how it is behaving. So that is, I feel that's kind of cool that it is able to learn. But why it is learning, is that your question? I guess.
Yeah.
So that's because it is very high dimensional parameters. So these models, they have more than 100 million parameters. Especially the EBSD one that I showed, it had I think it has around 250 million parameters. So it is highly the learning capacity is quite large. So if you have big data sets and of course big compute, you can minimize your loss function in many different ways and take advantage of those millions of parameters. And that's why it is learning better. But of course, you can always argue that if I make it billions of parameters, that I can always make it more and more accurate, and that's a fact. So there is always a trade-off between how complex you want to be able to go. Ideally you want a simplest possible model that is most accurate, but these things are always a trade-off.
Bryce.
Yeah, I had a question about the. I think on your demo you showed the fatigue strength predictor that it had uncertainty estimates. As I recall, that was not part of the original paper, so I was just curious what.
Yeah, that is something that we have added recently.
Okay. What UQ method is it?
So these are ensemble techniques. So we take an average of many different models.
Okay.
Anyway, so when we have many such predictions, that itself gives a measure of uncertainty. Just the standard deviation itself is one measure. But also we take into account the number of samples and the RMSE, because RMSE and standard deviation, they are the L2 norm kind of. So we combine them using T tables and standard statistics procedure.
Questions? Go on then, Alvin.
So in something like this, I mean, you're taking advantage of the fact that you have a number of known compounds, and the compound knows its chemistry, right? Fe2O3 has inherently oxidation state, whether or not you tell the computer it's an oxidation state. But one of the sort of keys is that where you pull your data from, your sort of formation energies, these compounds may not be, say, at ambient condition. They may be hypothetical predicted crystal structures. So do you go through a lot of additional effort to sanitize the data and make sure that these are indeed not predicted structures from?
Very, very important question. So we rely on the collaborators for that, and we have done that. So the results are not here, but there is a paper in preparation where we have actually scanned. So in 2014, we scanned the ternary space using these models because they're faster. Now we are scanning the quaternary space, and then we are trying to see that the predictions that we get. Of course, their predictions at 0 Kelvin because that's what the model has learned. But we are using domain knowledge to interpret the result, not to make the model. So, of course, you can say that in this case we know enough domain knowledge. So why don't you put it in the model? That's of course you can do, and possibly it will increase accuracy. But the point of this work is that in many cases we may not have domain knowledge. So what if we withhold domain knowledge on purpose and then see what best we can do? But of course, the insights that come out of it, they have to be analyzed by a materials expert. So Chris Roton's group, folks over there have done that. And that is in the paper that we're working on.
So it kind of follows up from other questions. So this question to do with the deep learning model for formation energy as well as the pavement crack detection model. So does the visualization of intermediate layers does it give you any new domain knowledge? Like you said that you're withholding domain knowledge and trying to test if it can learn its own. But beyond that, can it add to the knowledge just by visualizing these intermediate layers?
Excellent point. So I always say that a successful data mining project is when about half or little more than half of your insights are what you already expect, but there also should be some surprises. If everything that you get is already that you know, then it's okay, but it's you don't push it forward. So of course we do find a lot of things that we cannot explain. So some of the things like the groups were clustered, that's good, but some groups were kind of scattered also. So those can provide new avenues for more investigation, but again that requires domain knowledge to analyze that. So again we rely on collaborators. There's nothing right now that I can point out because this is still not published work.
Maybe time for one more short question. Yeah, Joe?
Hi, yes. I had a question actually about this with your deep learning model. There are so many things that you can, or actually, how many layers did you use? And by optimizing the number of units as well as your activation functions between layers and also at the end layer, did you use like a genetic algorithm to go between those and find a combination that gave you the highest percentage or the highest accuracy?
Sure. So in this particular case, what we did was we kind of explored a number of layers from very shallow, like starting from 1, 2, all the way up to 25. 25. So these are significantly deep, and of course, as you increase the number of layers, the error goes down. But we saw that around 17 layers or so, it was kind of plateauing. So the model that you see on the website is a 17-layer model. And all the parameters were, of course, there was a grid search on most of them. I shouldn't say all. Most of them were with the grid search. So because we have a lot of big compute now, we can kind of search at least for one problem at a time. What you are mentioning is very interesting, though, from the computer science point of view, because these networks, designing these networks is a black art kind of. There's no systematic. There are some systematic guidelines, but there is no way to tell that, okay, for this problem, this is the structure that will work for sure. So there is a lot of work that is going on in terms of both in our group and other groups where we are trying to parallelize these models so that we can run them in parallel on like hundreds of thousands of processors, like supercomputers. And also there is research on predicting the parameters of the neural network itself. So instead of predicting the property, I use a neural network to predict the number of layers that I should make a network on. So there's a lot of interesting research going on like that.
Okay, let's thank our speaker one more time.
Nice job. Thank you very much.
That's the singularity. That's what they call it.
If you like, you can screen capture it. You can do it from your computer. Thank you so much. So just take it off. Yeah, or just take it off. Okay, thank you so much. Great job.
Well, where's your water?
That's me.